Welcome back to Structural Analysis. Today we are investigating the influence lines for indeterminate continuous beams. Specifically, we will be analyzing a symmetrical two-span continuous beam supported by rollers at points A, B, and C. Each individual span measures exactly 5 meters, creating a total structural length of 10 meters. Our targeted objective in this session is to construct the influence line for the vertical reaction force acting at the middle support, support B. To ensure a highly detailed analysis, we will calculate the specific influence line coordinates across the entire structure at uniform 1-meter intervals. Let's break down the mathematical methodology. To isolate the influence line for the reaction at the middle support B, we execute Müller-Breslau's principle. We begin by removing the physical support at B, releasing its geometric constraint. Next, we introduce an upward vertical unit load directly at point B, setting our redundant reaction force RB equal to 1. This localized unit action deforms the structural system into an upward elastic deflection curve. According to the principle, the exact influence line coordinate at any arbitrary position x is given by the ratio of the localized deflection, yxb, divided by the absolute maximum displacement calculated at support B, denoted as ybb. We establish our spatial tracking coordinate x, measuring directly from the right-hand support, support C. Invoking vertical equilibrium and geometric symmetry, an upward load of 1 at B generates equal downward balancing reactions at A and C, giving RA equals RC equals minus 0.5. Using Macaulay's method, the internal bending moment expression at a section x equals minus 0.5x plus 1x negative 5. Integrating our governing differential equation once provides the structural slope relationship along with integration constant C1. A second integration yields the overarching deflection curve formula, introducing a second integration constant, C2. To calculate our integration constants, we apply real boundary parameters at the outer unyielding pin supports. Deflection is 0 at support C, where x equals 0, meaning constant C2 is 0. Similarly, deflection is 0 at support A, where x equals 10, solving for constant C1 as negative 6.25. Substituting these values establishes the explicit equation for the local deflection curve, yxb. Evaluating this expression exactly at the midpoint, x equals 5 meters, yields a peak deflection value, ybb, equal to negative 20.83 over EI. We can now finalize our primary ratio formula by dividing deflection equation at any section with maximum deflection equation at x equals 5 meters. By systematically entering our 1-meter intervals into our finalized ratio, we generate the numerical dataset. The influence line values begin at 0 directly over support C, steadily climbing to 0.568 at 2 meters, and reaching a maximum peak value of exactly 1 directly above the central support B, where x equals 5. Due to the symmetry of the continuous spans, the values mirror themselves beautifully down to 0 as the tracking load reaches support A. Plotting this reveals a smooth curve that accurately graphs how a moving unit load transitions weight onto the middle support. Thank you for watching this video on structural analysis.